Okay, so in this video, we're going to be talking more about nuclear stability and the types of radiation. So in the last video, we talked about how there is a force, the strong nuclear force that's needed for nuclear stability, because inside the nucleus you have a bunch of protons which have a positive charge, and positive charge tends to repel through what's called the electric force or the Coulomb force. Okay, that's part of the electromagnetic force, which is one of the four fundamental forces. Now, the electric force or the Coulomb force, whatever you want to call it, we'll in IB Physics 2 talk about why it's called the Coulomb force. It doesn't matter what you call it, though. But this electrical force only interacts between charged particles. And by charged particles, I mean a particle that has a charge. So, for example, protons and electrons both are charged particles. One has a positive charge, one has a negative charge. Neutrons don't have any charge. They do have mass, but they don't have any charge. And so, protons repel each other through the electrical force because they have charge, and then the strong nuclear force is a force that exists basically only inside the nucleus that helps hold the nucleus together. This force interacts between both protons and neutrons, and so it's not dependent on charge at all. Charge is not even a factor for the strong nuclear force, and therefore if you add neutrons to a nucleus, you can increase the strong nuclear force. And what you want is, and this is the key phrase in this bullet point right here, is it says in a stable atom, the electric force which repels the protons is balanced out by the strong nuclear force which interacts between both protons and neutrons. And so it's relatively common to see questions on the IB exam related to, what conditions are necessarily for a nucleus to be, or a nucleus or atom to be stable, and this is basically how you would word your answer. You would talk about how those two forces within the nucleus of the atom have to be balanced. Now, what happens if those two forces, the electric force and the strong nuclear force, what if they're not balanced? Then you have what's called a radioactive atom, otherwise known as an unstable atom. And so, going to the next slide, it says here, neutrons serve as a buffer between repelling protons. We talked about that before. What we see on the graph here is we basically, each of these blue dots here is a known stable atom. And on the x-axis we have proton number, and on the y-axis we have neutron number. Okay, now this red line basically represents a 1-to-1 ratio of protons and neutrons. Okay, so everywhere along this red line would be where you had an atom with an equal number of protons and neutrons. And what you see is that at low atomic numbers, for elements low on the periodic table, you have a lot of blue dots around that red line. As you go higher up in atomic number, that is, as you get to the right of this graph, you'll notice that most of these stable, or basically all of the stable atoms, are above this line. So, in other words, for heavier elements, you have to have more than one neutron for every proton in order to maintain stability. Now, it's also true that at some point, somewhere around atomic number 82 or 83, the line of stability stops. And what that means is there are no stable atoms after, I believe, atomic number 82 or 83. I've seen both of those accepted on IB questions in the past. Atomic number 82 is lead, which basically means that any element past lead on the periodic table, that is, any element with an atomic number greater than 82, is unstable, meaning radioactive. Okay, and the reason for that is just because at that point the nucleus has gotten so big that even more neutrons, even more strong nuclear force cannot help keep everything stable. Okay, so that's known as the line of stability, and I believe this is basically the same information, but the picture's not as good, so I'm just going to go past here. Now, we've talked about this before, but what it says on this slide, and again, please pause and take notes. It's really important that you take good notes in this unit, especially because there's a lot of conceptual stuff. Now, what it says here is it says nuclei which contain too many protons or too many neutrons, that is, if they don't have a balance between the strong nuclear force and the electric force, are unstable, which we call radioactive. Okay, so a radioactive atom is one with an unstable nucleus that spontaneously emits energetic particles or waves. And we kind of, collectively refer to those emitted particles or waves known as radiation. This bullet point, we talked about this before. For the purposes of IB physics, you need to understand that such radioisotopes are unstable due to an imbalance between the strong nuclear force and the electromagnetic force, or more specifically, just the electric part of the electromagnetic force. Now you might ask, what is a radioisotope? Well, remember that isotopes occur when you have elements that are the same, that is the same atomic number, but they have different number of neutrons. So that means a radioisotope is where you have, different isotopes, and one or more of those isotopes happen to be radioactive. So I think I named this example before, but carbon-12, carbon-11 and carbon-12 that make up our bodies for the most part are stable atoms. Carbon-14 is an unstable isotope, a radioactive isotope, so you could say carbon-14 is a radioisotope. It's an isotope of carbon that is radioactive, and if you've ever heard of carbon dating, that basically relies on the fact that carbon-14 is radioactive. And we'll talk more about that later. This instability in the nucleus results in these atoms emitting various types of radiation in an effort to become more stable. And so if I'm an unstable nucleus, my goal is to do stuff, and we'll talk about, what type of stuff can happen, but to do stuff because I want to end up as a stable nucleus. Okay, that is my goal if I am an unstable nucleus. Okay, so that's what this last bullet point is saying. Emitting various types of radiation in an effort to become more stable. And these are just examples of where you see radiation occur naturally. Bananas are radioactive because they have some potassium in them that is radioactive. Brazil nuts, tobacco. Your body, I said before, your body is made of carbon, and some of that carbon is the radioactive carbon-14. Smoke detectors have some, or not all smoke detectors, but many brands of smoke detector are built with radioactive material inside of them. And so there's naturally occurring radiation all around us. What we're going to talk about now is different types of radiation. Okay, so I'm going to skip on ahead a little bit and talk about three main types of radiation, okay, that can be emitted from radioisotopes. So we have alpha particles, beta particles, and gamma particles. And we will talk about each of these in turn. Again, please pause here and add this information to your notes. Now, these particles were named before their true identities were known. Alpha, beta, and gamma are the first three letters of the Greek alphabet, and so that is why they have the names they do. Now, nowadays we know their actual identities, and so as we go through each one at a time, we'll talk about what is an alpha particle in reality, what is a beta particle in reality. A lot of these things were given initial names before we actually knew more about what they were. And so these are the three types of radiation that are most commonly emitted by radioisotopes, and they are all consist of different types of particles with different properties. And so the first thing we're going to talk about is alpha particles. Now, later when I talk about alpha decay, if something is radioactive and it undergoes alpha decay, that means it's emitting alpha particles trying to become more stable. And we'll spend lots of time talking about what that process looks like when we go into writing decay equations. But for now, let's just talk about the properties of the three types of radiation. So let's start with alpha particles. Again, please pause here, add this information to your notes. In just a second, I'm going to write the symbol, the nuclear notation symbol for an alpha particle. Okay, so an alpha particle we now know is a helium nucleus. Now, there's two ways to commonly see alpha particles written. Either you write it as 4,2 He, okay, just because it is in fact a helium nucleus, or how you might have written it before you knew that it was a helium nucleus, 4,2 alpha. Okay, and so this little weird fish-looking thing that I wrote there is an alpha, or at least my way of doing an alpha. Okay, so 4,2 helium or 4,2 alpha. Either of those represent an alpha particle. Now, alpha particles, some things you should know about them. They do have a charge. They have a charge of +2. Protons have a charge of +1, so they have double the charge of a proton. And when it says it's a helium nucleus, a normal helium atom would have 2 protons, 2 neutrons, and 2 electrons. Okay, so an alpha particle is basically just 2 protons and 2 neutrons and no electrons. And so if you have 2 protons and 0 electrons, that is, if you only have the nucleus by itself, you have something that has a charge of +2. Now, it says mass is high. That is only relative to the other 2 types of particles, and we'll talk about those as we go. When it says penetrating power is low, what that means is penetrating power basically refers to how easily these particles travel through stuff. So alpha particles are very easily blocked by something as thin as your skin or a thin sheet of paper. Okay, it's not difficult to block alpha particles, which is good because they can be dangerous if they're not blocked. So if you're holding something that's emitting alpha particles, for the most part you're safe, if only because the dead skin cells covering your epidermis would block the alpha particles from going into your body and causing damage. Now, right here it says ionizing power is high. And so your first question when you read that is, okay, high, what does that mean? High compared to what? Well, high compared to the other 2 types of radiation that we're going to talk about. But more importantly, what does that mean? Ionizing power. Okay, ionizing power refers to the ability of a particle, and this is a term that's going to come up a lot in the future. So again, make sure you're taking really good notes. The ability of something to ionize an atom. Now, that doesn't really help you if you don't know what that means. So the ability of something to remove electrons from atoms. Okay, so if you take a neutral atom and you remove electrons, you get what's called an ion. Okay, you would get a positive ion if you remove electrons. And so to ionize an atom means to remove its electrons. Ionizing power basically is a measure of how easily the particle can do that. Now, alpha particles have a high ionizing power. And the reason they have a high ionizing power is because of their size and their mass. Okay, remember, they have a high mass. We talked about before how the mass of the electron is thousands of times smaller than that of the proton or the neutron. Okay, a helium nucleus, an alpha particle, has an even higher mass. Okay, so the analogy, if you want to compare, the alpha particle has a mass thousands and thousands of times larger than any electron. So if you imagine, like, here's a nucleus, and here's the electrons around. Oh, wow, I can't draw. Let me try that again. If you imagine an atom with a nucleus in the center, and here on the outside you have, let's say, electrons orbiting, and this particle comes in, an alpha particle comes in. If it hits that electron, imagine this is thousands of times more massive than this electron. Okay, so imagine, like, I don't know, a cannonball hitting a marble. Okay, but even a bigger size difference. Okay, this alpha particle is going to make that electron go flying. Okay, so alpha particles have a very high ionizing power because of their size, which is bad. We'll talk more about this later. Ionization tends to be very dangerous to living beings, just because our cells are made of, or our bodies are made of cells, and DNA and all that stuff, and ionization, knocking electrons out of cells or out of DNA tends to cause lots of issues, mutation, cell death, death, stuff like that. And so, generally speaking, when you see ionizing power in the context of, what does that mean for humans, that is basically bad. That is dangerous to human beings. Okay, which is why it's good that alpha particles, even though they do have a high ionizing power, they have a very low penetrating power. Okay, one example of where you would see maybe something that emits alpha particles would be in smoke detectors. Typically speaking, and I'll mention this later, but typically speaking, you see alpha particles only with very, very heavy atoms. Okay, so I'm going to erase this. Please pause it here if you need to write any of this down, and we're going to go on to the next one. Okay, beta particles. Okay, now, confusingly, there's actually two types of beta particle. Okay, there's what is called beta minus, and there's what's called beta plus. Okay, now a beta minus particle, we now know, we didn't know at the time of naming, but we now know a beta minus particle is an electron. Okay, now you know what an electron is, you probably don't know what a positron is. Okay, a beta plus particle we now know is a positron. So what is a positron, you ask? Well, I'm not trying to be glib when I say this, but a positron is a positive electron. Okay, that's where the name comes from, positron, positive electron. Now there might be somebody out there thinking, wait, isn't a positive electron just a proton? No. A proton and electron are vastly different types of particles. Okay, proton is thousands of times more massive than the electron. They're not even the same type of particle at the elementary level, and we'll talk more about that in IB physics too, but the proton and electron are vastly different. The electron and the positron have the exact same characteristics, the exact same mass. The only difference is that a positron has a positive charge and the electron has a negative charge. That is the only difference between a positron and an electron. At least the only difference we're going to talk about in this video. Okay, so how do you write that in nuclear notation? Well, because there's two types of beta particles, there's 4 different ways to write this. Either you can write it as an electron. I'm talking about beta minus here. So either you can write it as an electron, or you can use the beta symbol, which looks like this fancy B, like so. Okay, so this would be for beta minus. Now for beta plus, I'll do it over here so I have space, you can either write it as a positron, which a positron you'd use 0, 1, E, okay, just like an electron except it's a positive 1 instead of a negative 1, or 0, 1, beta, like that. And so that's how you write the symbol for beta particle in nuclear notation. Now, beta particles have a low mass. Because they're electrons, they have the same mass as electrons, obviously. They have a medium penetrating power. They can go through your skin, but if you have like a relatively thin sheet of metal like aluminum, that's enough to block beta particles. Their ionizing power is medium. Remember, ionizing power refers to the ability to remove electrons from atoms. And so basically you're hitting electrons with other electrons, which can work, but not as well as with alpha particles, which are much, much bigger. And so that's why we say beta particles, both beta minus and beta plus, have medium ionizing power. Now, one example of that would be carbon-14 undergoes beta decay to become nitrogen-14. And again, when I say undergoes beta decay, I mean carbon-14 is an unstable nucleus. We talked about what that means. It emits a beta particle, and then it becomes nitrogen. And we'll talk about that process later. But this, when you talk about carbon dating, this process right here, this carbon-14 turning into nitrogen-14, is a part of using that carbon dating that you might have heard of. So there's just one more we're going to talk about. I'm going to erase what's on the screen, so pause it here if you need to. And that is gamma. And gamma is probably the one you're going to see the least of just because it's not super exciting. A gamma particle is a high energy photon. Now a photon is a particle of light. Okay, so make sure you understand what that is. Okay, gamma particle is a particle of light. It has no mass. It has no charge. The symbol for gamma, there's only the one. It has no mass, no charge. Its numbers on the left side are 0, 0, and a gamma looks something like this. It's not the best gamma. Something like a weird Y-looking thing. If you just Google the Greek letter gamma, you'll probably find a better version of gamma than I can draw, but something like that. Maybe take off a little bit here. 0, 0, something like that. Okay, now the gamma particle is a high energy photon. If you imagine an X-ray, okay, you can have X-ray photons. A gamma particle is basically a supercharged X-ray. Okay, so it's in the same kind of class as X-rays. They have a very high penetrating power. Because they have no mass, they are the lightest of the 3 types of radiation. By the way, that's a pun in case you didn't recognize that, because they're particles of light. Of course, they're the lightest particle, but they have no mass, literally no mass. So it takes a lot of lead to block gamma particles. If you've ever gone to the dentist or you've gotten x-rays, they probably put something like a lead vest over you to protect you from the x-rays, because lead can block x-rays. And to some extent, lead can also block gamma particles, even though gamma particles have more energy. But it takes a lot more lead to block gamma particles. They do have a relatively low ionizing power, which is good because they can go through stuff very easily. You're not going to see gamma too much, but you do need to know, you do need to be able to recognize it. Most radioactive substances also emit gamma particles. And so it's possible for something to be radioactive and, maybe it's emitting alpha particles, but also gamma particles. And so that's a possibility. And again, this is probably the one you'll see the least often. Okay, so I'm going to erase this just to go through a little bit more. This chart is kind of, you can see the size difference when you're looking at these three, how alpha is way bigger than beta. Most mass, most ionizing. There's a little kind of pun right here. More mass allows particles to more efficiently transfer energy and ionize an atom, which, as we talked about before, that can be bad. This slide kind of shows you the difference in penetration power between alpha, beta, and gamma. When it says 5 centimeters in air, that means if something emits an alpha particle, it can basically go 5 centimeters in air before it gets blocked by something, stray dust in the air or something. And so alpha is very weakly penetrating, beta more penetrating, and then gamma is the most penetrating. This basically also shows the same thing. And then this chart right here is basically a summarization of the three types of radiation. Okay, alpha, beta, and gamma. Okay, so hopefully you got all of that. Again, pause it here if you need to add this information to your notes. You don't need to know about the typical speeds or anything like that, but you do need to know the other things. The relative mass values, you don't really need to know that, other than to know alpha is much bigger than beta or gamma in mass. Okay, so again, pause it there, add that to your notes if you've not already done so. I think this next slide is basically the same information. The chart's maybe not as nice looking, but basically the same information. And then just really quickly, add this to your notes. Pause it here if you need to write this into your notes. These are just some hints about the different types of radiation. Alpha decay occurs when a heavier nucleus has too many nucleons. Beta minus decay, a type of decay in which a neutron inside of a nucleus is transformed into a proton and in the process emits an electron, aka a beta minus particle, and an antineutrino. Okay, beta plus decay is very similar, except it's a proton turning into neutron, and in the process emitting a positron, aka a beta plus particle, and a neutrino. Now you might be asking, wait, neutrino, did he misspell neutron? No, neutrino and neutron are vastly different particles. They both don't have any charge, but besides that, they're vastly different. But we will talk more about that in the next video. I just wanted to kind of tease you with that at the end. I will go over, a little bit more about what that means as far as the antineutrino and the neutrino in the next video. My plan in the next video is to talk a little bit more about these types of radiations, and then we're going to get into writing decay equations. And writing decay equations is really important because that's going to be the foundation for other things like nuclear fission, nuclear fusion, transmutation, stuff like that. Okay, so please let me know if you have any questions. I'll see you in the next video.